Dear learners, in this lecture we are going to discuss a very important topic in process plant piping design, that is the line sizing. So in any process industry, whether it is an oil and gas, chemical processing, power plants or water treatment facilities, the correct size of the pipe is very crucial, and it will ensure the smooth operation, process efficiency, and the cost effectiveness of the piping systems. So, the line sizing plays a very important role in the fluid transportation by ensuring that the process is running efficiently and cost effective manner. The fluid transport is very important in process plants, without which we cannot run any reactors or separation systems and so on. So if the pipes are very small, there will be very high pressure drop, which will increase the energy consumption, and the possible flow restrictions may occur. If, on the other hand, if you look at very large pipelines, that will lead to excessive material cost, space constraints, and the inefficiencies in fluid transport by not having a fully developed flow inside the pipeline. So, the large pipelines will lead to excessive material cost, so that increases the capital cost of the investments. So, to have a balanced performance, safety, and cost considerations, we need to go for a proper line sizing. So it is very important in any process industry that the pipeline sizes has to be properly calculated with suitable allowance for the safety, and to ensure that there is less pressure drop and pumping cost with minimum of flow restrictions. So the pipelines should be of the adequate size to ensure a proper fluid flow in the process plant. What is line sizing? So define line sizing. It refers to a process of determining the appropriate diameter of the pipe used to transport fluids, liquids, gases, or multi-phase mixtures in a system. The characteristics of the multi-phase systems, gases, and liquids are different. So, we need to consider such differences in fluid characteristics while choosing or sizing the process line. So, determining the appropriate diameter to transport these fluids is known as the line sizing. When you determine the correct pipe size, it will ensure that the fluid is moving efficiently without excess pressure drop or some velocity related problems like hammering and pipeline erosion. So because of high velocity in the pipelines, if you have a smaller diameter of the pipelines, there will be erosion related problems which affects the pipeline thickness. So over a course of time, the reduced thickness will affect the pressure limits of the pipeline. So the pipeline may fail at the areas of erosion, and it can cause safety issues. So by ensuring a correct pipe size, the fluid is moving efficiently without excessive pressure drop or some velocity related problems. So in process industries, you have to select the pipe size based on certain criteria. First is, what is our flow requirement? Whether the pipeline can withstand the required flow rate, and what are the pressure drop limitations that is need to be satisfied. Then The phase of the fluid, whether it is a gas or a liquid, whether it is having a high viscous or less viscous, high dense material or low dense material, along with the corrosive characteristics, the compressible nature or incompressible nature of the flow, all these things comes under the fluid properties which needs to be considered while doing the line sizing. Next is the material and installation cost, which needs to be worked out for different types of materials suitable for our application. For example, we may go for alloy based materials, or we can use the line with some cladding or some coverings which may prevent the erosion or the corrosive damage. So the economic considerations involves the various materials and the installation cost that is associated with that. So we need to work out the entire costing before choosing the material and installing the pipeline. Next is we need to go for the proper process and safety standards. So a proper line sizing will ensure that the system is operating with acceptable pressure drop and velocity limits. So this will prevent the energy loss, then cavitation, then vibration effects, noise during the transport, and erosion. So erosion is due to high velocities, noise is also due to very high velocities, vibrational loads may be induced by the hammering, cavitation is due to very small diameter of the pipelines with high pressure drop, so that the fluid vaporizes and creates micro bubbles inside the pipeline. So the cavitation effects are predominant when you do not satisfy the NPSH requirements. So the cavitation is a very troublesome phenomena where the cavitation or the collapse of the microbubbles on the walls of the pipeline will be inducing small spots or the reduction in the thickness of the pipeline wall, and energy losses due to the pumping and the friction effects that are in place also in increases the operating cost. So when you have a proper line sizing in place, we ensure that the system is operating within the velocity limits and acceptable pressure drop limits, so that you prevent these problems of erosion, noise, vibration, cavitation, and energy loss. Next is the importance of line sizing. The first point is an optimized pressure drop. So if you have a properly sized pipe that minimizes the excessive pressure drop, we can ensure that the pumping cost and the compressors do not have to work harder than necessary, because if you have a properly sized pipe with proper velocity and flow rate calculations, we do not have to worry about the increased cost of the pumping. So to pump a fluid through a smaller size pipe, we require excessive energy. So we need to appropriately size a pipe to ensure that the pumps and compressors do not work harder than necessary. So this will reduce the energy consumption and improve the process efficiency. Next is the control of fluid velocity. So if you are having a high fluid velocity, that can cause erosion, then noise, vibration, and excessive friction loss. Because high fluid velocity means high value of Reynolds number, since the Reynolds number is the ratio of inertial forces to the viscous forces. So when you are having a high velocity, it indicates the high value of Reynolds number. Since the Reynolds number can be given as a function of the friction factor, can be a function of the Reynolds number. As per the Moody's chart, high fluid velocities will increase the friction losses. Then, in case of a multi-phase flow, when you are transporting some slurries where you have some settled solids or undissolved solids, the low velocity of the fluid can result in the sedimentation or the settling of the solids in the uh, pipeline, and there can also be slugginess in the flow where the flowing fluid are transported as slugs, and there can be phase separation issues during the multi-phase flows. And the major problem with low velocity when transporting the slurries is the settling of the undissolved solid on the walls of the pipeline. So that can result in some scaling and improper flow considerations when transporting the low velocity slurries. Then cost effective design. Larger pipelines will require more material, space and support structures and increasing capital cost. So the smaller pipes can reduce the cost, but it can lead to higher operational expenses due to the increased pressure drop. So to ensure a cost effective design, we need to optimize the pipe diameter so that it does not occupy more space, more material, and require support structures, which will increase the capital expenses. But on the other hand, if you go for a very small pipeline, it may lead to higher operational expenses due to increased pressure drop. Next is we need to ensure the safety and compliance by following the ASME B31.3, that is the process piping code, then API and ISO guidelines. So by following these guidelines for the line sizing and also to the testing and material specifications, it will reduce the risk of pipe failure, then leak and operational hazards during the transportation of the process fluid. A proper pump and compressor selection will also be necessary, and choosing the correct pipe size will aid in the NPSS calculations, and selection of the appropriate pumps and compressors and control valves. So that will ensure the efficient operation and the longevity of the lines. The various factors that will affect the line size. First is the flow rate. So the flow rate is the value with which you start the line sizing calculations. It will determine the pipe size to ensure the smooth transport. Normally, we measure the flow rate as in terms of the meter cube per hour, that is the volumetric flow rate, or we go for the uh, liter per minute or gallons per minute for liquids, and in the case of gases we go for standard cubic feet per minute or meter cube per hour or normal meter cube per hour for gases. Then the flow rates, normally we consider the volumetric flow rate when determining the line sizing. Even if we have the mass flow rate, that can be converted to volumetric flow rate by dividing it with the density of the process fluid. Next is the fluid properties, where you have density, viscosity, then compressibility factors, the phase of the process fluid, whether it is a liquid, gas, vapor, or multi-phase lines, may impact the line sizing. To minimize the friction losses and the viscous effects, the viscous fluids will require a very large diameter pipeline, and the operating pressure and temperature may also influence the line size. If you have higher pressure and temperatures, we have to go for higher scheduled ratings to withstand the thermal stresses and the pressure forces. The various stresses that may be experienced by the pipeline will be the thermal stresses and the compressive stresses and wind loads and other seismic considerations. So those operating pressure and temperature will also influence the schedule number of the line size. So we can have two different diameters and different schedule numbers. So the pressure rating and the temperature rating will decide to go for either thicker walls to withstand the stresses or to go for a lesser schedule number. Then thermal expansion considerations also needs to be considered while doing the pipe sizing and the layout of the piping. So to consider or to accommodate for thermal expansion, we normally go for the bends and the horseshoe kind of a bend arrangement, and we go for bellows to counter the thermal expansion considerations. So this will also affect the pipe sizing and the layout of the piping. Next is considering the allowable pressure drop. The typical values of the pressure drops will be for liquids 1 to 10 pounds per square inch per 100 feet of the pipe, and for gases it has to be 0.5 to 2 pounds per square inch per 100 feet of the pipe. If we have excessive energy losses and the system performance will be very poor, it will affect the transportation of the fluid because of the energy losses. The pressure drop will be very high. So if there is a very high pressure drop, there will be a lot of energy losses which may result in the inadequate flow velocities. So the pressure drop limits are to be set to prevent the excessive energy loss, and the typical values for liquids and gases are given for 100 feet of pipe. Next is the velocity constraint. As told earlier, you need to control the liquid velocity or the flow velocity to prevent the erosion, cavitation and noise effects. The general velocity limits for water-like fluids, it will be 1 to 3 meter per second, and in the case of viscous fluids, the transportation velocity is in the range of 0.5 to 1 meter per second. In the case of gases, the general velocity limits are 10 to 30 meter per second for air, natural gas, and in the case of steam, we go for a velocity limit of 5 to 15 meter per second. Then the economic considerations involve the pipe material, installation cost and maintenance in selecting a very economically feasible size of the process plant pipeline. So how to do the line sizing? These are the steps that needs to be followed for doing the line sizing. First, we need to know the flow rate of our operation or the flow rate of the fluid transport. So for that particular flow rate, you need to select an acceptable velocity range as given in your previous slides, depending upon the fluid nature of the fluid and the fluid properties. You select an acceptable velocity range. Then using the value of the flow rate and the acceptable velocity range, you can calculate the pipe diameter from the continuity equation, that is Q, that is the flow rate will be equal to the cross-sectional area of the pipeline into the flow velocity. So calculate the pipe diameter using the continuity equation. Q is equal to A into V. After calculating the pipe diameter, we need to check for the pressure drop using the Darcy-Weisbach equation, whether the pressure drop is within the allowable limits. Before determining the pressure drop using the Darcy-Weisbach equation, we need to know the value of friction factor. So to calculate the value of or to find out the value of friction factor, we need to use the Moody's chart. Moody's chart gives the relationship between friction factor and the Reynolds number. So calculate the Reynolds number for the value of pipe diameter, fluid property of density, viscosity, and the flow velocity. So the Reynolds number is calculated as dV rho by mu, which is the inertial effect by the viscous effect, and decided whether the flow is turbulent or laminar. So accordingly, with the value of the calculated Reynolds number and the flow regime, you go for the value of the friction factor from the Moody's chart. That value of Darcy's friction factor is substituted to check for the pressure drop. So once the pressure drop is determined and if it is within the acceptable limits, then the pipe diameter that is calculated is considered as the line size. Otherwise, we need to change the value of the pipe diameter and or we change the value of an acceptable velocity range to determine the next size of standard pipe diameters that may be available. Next, once the pipe diameter is fixed, we need to refer the pipe schedule to consider whether the thickness of the pipe will withstand the pressure and the thermal stresses that may be happening during the course of operation, and the pressure ratings and the pipe thickness is decided by referring to the pipe schedule chart. Then we need to ensure the compliance with the codes and standards available. Especially we need to look for the API codes to consider the material specifications, and we need to look at B31.3 codes for the process plant piping to ensure that our calculated line size is in compliance with the codes and standards available for process plant piping. So to repeat the line sizing methodology, first is the given flow rate, you determine or we design the line size or calculate the line size for a given flow rate. You select an acceptable velocity range from the table as given by the guidelines depending upon the nature of the process fluid, whether it is viscous or whether it is non-viscous or a fluid having as water or any process fluid, whether it is dense or so. You select an acceptable velocity range, then calculate the pipe diameter from the continuity equation Q is equal to A into V, then determine the Reynolds number, and from the Reynolds number you find out the friction factor using the Moody's chart. Then using the value of friction factor, you check for the pressure drop using the Darcy-Weisbach equation. After you fix the pipe diameter for an allowable pressure drop, refer to the schedule numbers for the pipe thickness and the pressure rating. Ensure the compliance with the various codes and standards that are available to have a very safe line size. A few examples uh, of line sizing implications. First is an example of pump discharge. So if you have a very small pipe, it can cause high pressure drop. When high pressure drop is present in the smaller pipeline, it can lead to the cavitation in the pumps. So cavitation in the pumps is a very important or a very problematic issue which will affect the interior casing, pump casing. So the micro bubbles will hit those impellers and the interior casing, which can lead to damage of the pumps. So if you properly size a pipeline by considering the NPSH requirements, then it will ensure an efficient pump performance. Uh, in the case of a steam distribution piping, if your steam lines are undersized, in a process plant, if you have a steam line, those are undersized, the velocity of the steam traveling inside a very small diameter pipeline will be high. So if you have an inadequate line size for the entire process plant, in the case of steam lines, there will be high velocity steam traveling in those undersized pipelines. So this will cause erosion and pressure losses, which will affect the performance of the heat exchangers. So if there is pressure loss when the steam is passing into the heat exchangers, there will be less uh, heat transfer because of inadequate steam flow in the uh, heat exchangers. So if you ensure a proper line size, it will reduce the energy loss and it maintains the process efficiency. In the case of compressed air systems, there might be pressure fluctuations due to undersized pipes. This will affect the pneumatic tools which depend upon compressed air for their operation, and pneumatic control systems also depend upon the compressed air systems. So if there are pressure fluctuations, there might not be a proper control implemented due to the undersized pipes. So the correct sizing will minimize the energy consumption, and it improves the reliability of the fluid transport. In the case of compressed air systems, it will be air. Next, a few more examples. For example, if you consider pressure drop in a compressed air system, uh, we identify the problem as an undersized air distribution line. So that is causing high pressure losses. So if you increase the compressor power in such a case, it will raise the energy cost unnecessarily. So what needs to be done here? You can increase the air distribution pipe size so that you can maintain the pressure at all the endpoints, and also you can install additional storage tanks to store the compressed air at strategic locations in order to balance the pressure fluctuations and the supply demand fluctuations. So in case of pneumatic tools and automation requiring compressed air, we have to ensure that the line is not undersized, so that the distribution lines will be free from high pressure loss, and also the air distribution pipelines can be having a greater diameter to maintain the pressure with low pressure losses at all the endpoints. The next example which may be considered here is a refinery's cooling water system. It is suffering from inefficient heat transfer and pump overloading. So pump overloading may be caused due to high velocity and friction losses. So because of that, when a pump is required to transport the fluid at a high velocity, then the pumping requirements is very high. The energy cost also increases. So the pump may be overloaded and forced to operate beyond its rated capacity. In such case, we can have to reduce the velocity below 2 meter per second for the water low. So to reduce the velocity, the solution is to install a larger diameter pipe. So when you install the larger diameter pipe, the flow velocity can be maintained at about 2 meter per second, which can minimize the friction losses and reduce the pump load. So inefficient heat transfer may be minimized because when the fluid flow is happening at a low velocity, there is sufficient time for the heat transfer to take place and the exchange of heat energy. This will increase the efficiency of heat transfer and prevent the pump overloading. Then the compressible flows are different from the incompressible flows. So there are a few more considerations when designing pipe sizes for compressible flows, especially the gases and vapors, because they will experience changes in density, velocity, and pressure as they travel through a pipeline. So the various key principles that will govern the compressible flow, we need to use the gas law relationship. Most gases, they behave ideally. We can use the ideal gas law for certain temperature and pressure ranges. That is the PV equal to nRT relationship. Unlike liquids, the gases will expand and contract significantly with pressure changes. So this ideal gas law equation is used with caution for a certain temperature and pressure range. Next is depending upon the Mach number. This Mach number is calculated to decide whether the flow behavior is close to incompressible or compressible. Mach number is given as the ratio of gas velocity to the speed of sound, and if the Mach number is less than zero point 0.3, we may consider the gas to behave like an incompressible fluid, and if the Mach number is greater than zero point 0.3, then we need to consider the compressibility effects. A very important condition for compressible flows is the choked flow condition. The choked flow condition or which occurs at the sonic limit. So that is when the gas velocity is equal to the speed of the sound, that is the Mach number value is equal to 1. The further pressure drops do not increase the flow rate. The pipeline is entirely choked with the maximum mass flow rate at the sonic limit condition or the choked flow condition. So that particular size of the pipeline can no longer accommodate more number of mass inside. So the maximum mass flow rate that can be calculated for compressible flows will occur at the value of Mach number equal to 1. The pipeline designer should ensure that the choked flow condition is not reached while designing the pipelines. Choked flow can happen in nozzles, pressure relief valves, and high velocity pipelines when the fluid is released at a very high velocity in nozzles and pressure relief valves. So we need to consider the maximum mass flow rate that can be accommodated in a pipeline, and depending on that we need to do the line sizing. Then a few equations that may be used for compressible flow calculations is the Weymouth equation that is used for the long transmission gas pipelines. Here the flow rate Q is given as 3.17 multiplied by the diameter or the inside diameter of the line to the power of 2.667 multiplied by the difference in pressure, which are squared, divided by the length of the pipeline, temperature, and the compressibility factor Z whole to the power of 0.5. So this Weymouth equation is applicable for gas pipelines which are transporting the fluid for a long distance, and in any general case we can use the general gas flow equation to determine the inside diameter. If we know the values of the flow rate, then compressibility factor, and the flow coefficient C, P1 and P2 will stand for the entering and the exit pressure values. So the general gas flow equation, the diameter of the gas line, that is inside diameter D, will be equal to 144 multiplied by the compressibility factor RT divided by pi square P1 into P2 multiplied by the flow rate to the divided by the flow coefficient C squared whole to the power of 0.25. So in short gas pipelines, we may use the Darcy-Weisbach equation to calculate the pressure drop. In the case of short gas pipelines, we do not go for any other empirical equations. We can use the Darcy-Weisbach equation for short gas pipelines.